This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is the change in dimension of a thin cylindrical shell when it is subjected to some internal pressure in mechanics of solids. Then the cylinders having number of applications in industries, particularly for transportation of fluids as well as the gases, as well as the storage purpose and boilers and so on. When storage as well as the transportation of fluid or gases, the internally the fluid is exerted certain pressure over it now. Because of fluid pressure now, the cylinders are subjected to three types of stresses. Hoop stresses, or it is also called circumference stresses, longitudinal stresses, and the third one is radial stresses. The first two are called now hoop stresses and longitudinal stresses. They are in tensile in nature, and the radial stresses is in compressive nature. Since the magnitude of radial stress when comparing with hoop stress as well as the longitudinal stress in the case of thin cylinder is very negligible because of having the cylinder thickness very less. These are neglected now. That means in case of thin cylinder, we have to consider only two types of stresses. One is hoop stress, the second one is known as longitudinal stresses. Here the thin cylinders generally failures occurs just because of two types. One is nothing but divided into two troughs as shown in the figure. The second one is it is split into two cylinders now. The first case is nothing but it is only because of circumference stresses that is there. That is, if the fluid pressure is behind the permissible limits, that the failure occurs in the case of split into two types. It is only because of circumference stresses induced in it. The second one is known as the pipe is split into two cylinders now. This is only because of longitudinal stresses. So here the figure is representing the failure of pipe due to the circumference stresses. It is also called hoop stress. The magnitude of stress that is induced because of internal pressure P when it is there inside the cylinder is given by PD divided by 2T now, where P stands for the fluid pressure, D standing for diameter of the internal diameter of the pipe, T is representing the thickness now. In case of longitudinal stress, the amount of stress that is induced is given by PD divided by 40. Here it is given. But in the case of previous circumference stresses, it is equal to PD divided by 2T. That is, the longitudinal stress is equal to half of the circumference stresses. Hence, for the design point of view, only circumference stress is considered. Design means nothing but here what is the amount of pressure that it can be allowed, or what is the diameter of the pipe or thickness, whatever the data that is required for designing that particular cylinder. Is only considered only hoop stress, not the longitudinal stresses. Here, while designing, the thickness can be determined by using the relations. Now, here we are having sigma C is equal to, we are having equation to PD divided by 2T now. From these relations, we can determine the thickness of the pipe that is required is given by, that is equal to PD divided by 2 sigma C and so on. That is what is the content that is required. Specification required that can be considered or determined by using only hoop stress relations. Because of these stresses, already we discussed the longitudinal stress as well as the circumference stresses, both are in tensile in nature. Hence, the dimension in the direction of stress that is acting, it increases now. That is the diameter as well as the length of the pipe, that is length of the cylinder, both are increases because of longitudinal as well as the circumference stresses. Here we have to determine what is the change in dimension of the cylindrical shell as well as the volumetric strain. So first consider, let L is representing the length of the shell now, D is representing diameter of the shell, T thickness of the shell, and P the intensity of the internal pressure or the fluid pressure inside the cylinder. So according to the previous relations we are having, the circumference is given by sigma C is equal to PD by 2T. it is acting just a perpendicular to the diameter now along the length direction. That means if you take the pipe in nothing but if it is having half like this after splitting into, this is nothing but directions we have to take it now. But it is acting just nothing but here perpendicular these directions. Entire its length, that is the affected area is equal to, we can take it as diameter multiplied by thickness. This is nothing but the area. That is pressure divided by, here we can take it as the area is equal to d by t and so on. These are the general equations we are taking now. So this is the representing the here now pressure as well as the area nothing but this one now. In longitudinal, because of circumference stresses, it is divided into two troughs as shown in figure like this now. The second one is longitudinal stress. The longitudinal stress is given by sigma L is equal to PD divided by 40. As in delta L is equal to, because of the stresses which are inducing, one is circumference stresses as well as one more longitudinal stresses, the dimensions also changes in the direction of stresses are acting. Let delta D is representing change in diameter of the shell and delta L is representing change in length of the shell and 1 by m is representing the Poisson ratio. So the change in diameter and length may be found out from the above the equations as usual, that is multiplied by strain and the corresponding linear dimensions. Here strain is equal to stress divided by strain is equal to, it gives Young's modulus now, generally it is represented E now. We can write the strain is equal to stress divided by Young's modulus. Strain nothing but a change in diameter divided by diameter, it is equal to stress divided by Young's modulus now. That is, by using this relationship we can determine what is the change in diameter as well as the change in length of the pipe now. Now first we are determining the change in diameter now. So it is equal to delta D is equal to, we can write it now, epsilon 1 dot D now. Because here now strain is nothing but a change in diameter divided by the original diameter. So here original change in diameter is equal to strain multiplied by the D now. So first I am taking this epsilon 1 is representing the strain which is produced along the diameter now. So which is equal to, because we have to consider the lateral strain also. Lateral strain, when longitudinal strain is acting, it is always acting in opposite directions. No, that is dimension decreases. Hence the net result that is increasing in diameter is given by the equations PD divided by 2TE 1 minus 1 by 2M. This is known as here strain that is produced. Here multiplied by D now. From this relation we got PD square divided by 2TE 1 minus 1 by 2M. This is known as change in diameter now. Similarly, the change in length is given by here epsilon 1 into L now, which is equal to PD divided by 2TE 1 by 2 minus 1 by M into L now. From this relation we got PDL divided by 2TE 1 by 2 minus 1 by M now. Okay, these are the change in dimensions now. This is based on this one, we are taking one problem here now. A cylindrical thin drum 800 mm in diameter and 44 meters long is made up of 10 meter thick plates now. If the drum is subjected to an internal pressure of 2.5 megapascal, determine its change in diameter and length. Take E equal to, that is Young's modulus is equal to 200 gigapascal and Poisson ratio is 0.25 now. Now from this problem the given data is a cylindrical thin drum 800 mm diameter given, that is diameter of the drum is equal to 800 millimeters and 4 mm long, 4 meters long, length of the cylinder is equal to 4 meters. But we have to convert all the dimensions into a single unit now. We are converting into here mm, which is equal to 4 meters is equal to 4 into 10 to the power of 3 mm now. The thickness of the plate is given, if the drum is subjected to here thickness of the plate is given 10 mm. So it is equal to 10 mm is given now. Poisson ratio is equal to 1 by m. Generally it is represented. It is values is equal to 0.25 now. The internal pressure of the fluid is equal to P is equal to 2.5 megapascal. It can be written as 2.5 Newton per mm square now. The modulus of velocity is given 200 gigapascal, which is equal to 200 into 10 to the power of 3 Newton per mm square now. Now the change in diameter is equal to, according to the previous relations, we are having PD square divided by 2TE into 1 minus 1 by 2 m now. And substituting these values, we got here P is equal to internal pressure equal to, we are having 2.5 Newton per mm square now is given. Here D is equal to 800 mm is given term diameter divided by here 2T, 2 is there, thickness is equal to 10 now, and E is equal to 200 into 10 to the power of 3 is given into 1 minus 1 by 2, m is equal to, we are given just 0.25, and doing the calculation we got this value is equal to 0.35 mm. That is because of this pressure now, the diameter increases by length of 0.35 mm. The change in length delta L is equal to PDL divided by 2TE into 1 by 2 minus 1 by m now, where P stands for the pressure, internal pressure of the fluid, D representing diameter of the thin cylinder, L is representing the length of the pipe, divided by 2 into T representing thickness of the shell, E representing the Young's modulus, 1 by 2 minus 1 by m, 1 by m is representing the Poisson ratio now, which is equal to, here P is equal to 2.5 into D is equal to 800 and L is equal to 4 meters, 4 into 10 to the power of 3 divided by 2T, 2 into T, E is equal to 200 gigapascal is given, which is equal to 200 into 10 to the power of 3, 1 by 2 minus 1 by m is equal to 0.25 now. By using this relations, we got this value is equal to 0.5 mm now. So that means because of this pressure now, the diameter increases by the length of 0.35 and its length by 0.5 mm. Okay, change in volume of a thin cylindrical shell. Because just we observed in the previous problems, because of longitudinal strain as well as the circumferential strain now, the length as well as the diameter of the shell increases now. Because of increasing dimensions, so overall the volume of the cylinder also increases. Here we have to determine what is the volumetric strain. Volumetric strain is defined as the ratio of change in volume divided by its original volume, or it is the ratio of change in volume to its original value. We have to determine that values how much it is now. Here, in order to determine the volumetric strain, first we are considering L is equal to that original length of the cylinder, D is representing the diameter of the cylinder, delta L is equal to change in length due to pressure, and the delta D is representing the change in diameter due to the pressures now. The original diameter, if it is there inside like this cylindrical shell, it is there, and I am taking like this, it is there. Now, the original volume is equal to, we can take it as the area multiplied by the, that is the length now, that is cross sections. How much it is here now? Pi by 4 D square into L. L is nothing but representing the here length of the cylinder now. This is called original. It is nothing but before, when the cylinder is not subjected to any internal pressure now. The final volume is equal to, according to our previous discussions, the diameter as well as the length both are increasing now. So assume just already we have taken delta L is representing the change in length as well as the delta D is representing the change in diameter. So which is equal to pi by 4 into D plus delta D whole square into L plus delta L now. The change in volume is equal to final volume minus initial volume. It is given by pi by 4 into D plus delta D whole square into L plus delta L minus half pi by 4 D square. So on doing expansion now, we got it is equal to pi by 4, we have taken the common word now, which is equal to D square plus delta D whole square plus 2D into delta D into L plus delta L minus of pi by 4 d square. Here from this relation, so we have taken delta d is nothing but very small now. As in just according to the previous case, we got this is nothing but equal to 0.3 mm. So delta d into delta d is equal to, when we are taking it is equal to 0.3 multiplied by 0.3, it is equal to 0.09 mm now. So 0.09 mm is nothing but smaller values. Hence, for approximation point of view, these values are neglected now. That is here the same equations now, pi by 4 d square delta d square 2d into delta d into L here plus pi by 4 d square delta d whole square 2d into delta d into delta L minus of pi by 4 d square into L now. This is nothing but values which are represented in color. These are nothing but multiplication of that increment, that is the change in length as well as the diameter. The product becomes very less when comparing with the original values. Hence, these are neglected now. Hence, the remaining values are now pi by 4 into d square into L plus 2dl into delta d plus pi by 4 into d square into delta L minus of pi by 4 d square now. From this relation now, here pi by 4 d square into L when we are taking now these values, the remaining values is equal to here now pi by 2 d square, both are get cancelled now. The remaining values is pi by 4 into 2dl minus into delta d plus pi by 4 into d square into delta L now. So the remaining values from this relation we got pi by 4 into 2dl into delta d, these equations, pi by 4 into d square into delta L, this equation, which is equal to pi by 4 d is the common word we have taken now. The remaining values is 2 into delta L into 2L delta d plus d into delta L now. The volumetric strain is defined as the change in volume to its original volume. This is representing the change in volume of a cylinder when it is subjected to some internal pressure now. So volumetric strain is equal to change in volume to original volume. So this is the change in volume. Original volume is already we calculated, the values is equal to pi d square into L values now. Pi d square by 4 into L now. So by substituting these values now, pi by 4 d into 2L into delta d plus d into delta L, this change in volume, divided by original value is equal to pi by 4 into d square into L now. Both are get cancelled because of it is a common constant in denominator as well as the numerator now. Just on expanding these equations now, we got 2L into delta d plus d into delta L divided by dl now. Or it can be written as now 2 into L delta d divided by d into L plus d into delta L by d into L now. Or on simplification we got this L get cancelled now. Here dd get cancelled now. The remaining values is equal to 2 into delta d by 2 delta d divided by 2 now plus the second delta L by L now. This delta d by d is nothing but representing the strain which is produced along the diameter, that is circumferential stress now. So it can be written as 2 into EC. Delta L by L is equal to the strain produced in the direction of length, that is epsilon L now. R which is equal to delta V is equal to change in volume is equal to, when we are doing cross multiplication we got V into epsilon L plus 2 epsilon C now. So by using this equation we can determine what is the change in volume of a cylinder when it is subjected to internal pressure, and also what is the strain, that is volumetric strain, that is produced within the cylinder. So based on the change in volume of a thin cylinder, this one problem we are taking now. A cylindrical vessel of 2 meters long and 500 mm in diameter with a 10 mm thick plates is subjected to an internal pressure of 3 megapascal. Calculate the change in volume of the vessel. Take E equal to 200 gigapascal and Poisson ratio is equal to 0.3 for the vessel's materials. Here given data is equal to length of this cylinder is given 2 meters long. We are converting all the dimensions into millimeters, which is equal to 2 into 10 to the power of 3 millimeters. Diameter vessel is equal to 500 mm. thickness is given 10 mm, and internal pressure is given 3 megapascal. 1 megapascal is equal to 1 Newton per mm square. So which can be written as 3 Newton per mm square. And the modulus of velocity is equal to 200 gigapascal. It can be written as 200 into 10 to the power 3 Newton per mm square now. And the Poisson ratio generally is represented by 1 by m, which is equal to 0.3 now. Now, what we require now? Calculate the change in volume of the vessel required now. Here, first of all, we have to determine the circumferential stress strain as well as the longitudinal strain now. So, circumferential strain is given by the change in diameter of the cylinder to its original diameter. That is the epsilon d divided by d now. It can be written as now PD divided by 2Ta 1 minus 1 by 2m now. From this relation we got to EC is equal to delta d by d is equal to, and substituting the values, 3 into 500 divided by 2 into 10 into 200 into 10 to the power of 3 into 1 minus 1 by 2 into 1 by m is equal to 0.3 now. And substituting these values we got this value is equal to 0.32 into 10 to the power of minus 3 now. Longitudinal strain is equal to the change in length to its longitudinal strain is equal to the change in length to its original length. The relation is PD divided by 2Te into 1 by 2 minus 1 by m. So substituting P is equal to A down 3 given, D is equal to 500 divided by 2 into thickness is equal to 10 and E is equal to 210 to the power of 3 multiplied by 1 by 2, 1 by m is equal to 0.3 now. So this value is equal to 0.075 into 10 to the power of minus 3 now. The original volume of the vessel is equal to V is equal to pi by 4 d square into L now. From this relation pi by 4 d is equal to 500 whole square into length is equal to 2 into 10 to the power of 3 now. From this relation we got 392.7 into 10 to the power of 6 mm to the power of 3 now. The change in volume is equal to delta V is equal to, it is the product of volume because till now we measured delta V divided by V is equal to 2 into epsilon D plus epsilon L we are taken now. So from this relation delta V is equal to V multiplied by 2 epsilon D plus epsilon L now. The same relationship we are taken here now. From this relation we got to V is equal to that original volume of the cylinder 392.7 into 10 to the power of 6 and EC is equal to 0.3 into 10 to the power of minus 3 plus L is equal to given 0.0075 into 10 to the power of minus 3 but it multiplied by 2 because we given 2 into epsilon L now. From this relationship we got this value is equal to 185 into 10 to the power of 3 mm to the power of 3. This is the given answer now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.